Okay, now let's look at some specific solutions around around some of the functions. Are the functions themselves are fairly realistic, but also they're nice in the sense that they're the math around them is a little bit easier. So some of the specific solutions, so some specific f sub x's, let's say f's, some specific functions. Okay, so these functions that obey the traveling wave equations can be in the form of cosines and sines and exponential functions. And so these are like functions that we see a lot. And sometimes you have a sine wave or cosine wave going through your network, and this is E sub j as a way to show to have a combination of cosine sine waves. Square waves, you can use Fourier decomposition, sort of Fourier analysis, to decompose a square wave, like a digital signal, into the sum of sine or cosine waves at different frequencies. Anyway, a legitimate function that we can look at is the cosine of omega t plus or minus beta z. And this looks like a traveling wave type of function. We have this t, some constant times t plus minus some constant times z. So that looks like a traveling wave solution, or also a sine of omega t plus or minus beta z, or e to the j omega t plus minus beta z. And so all of these things are sinusoidal waves that satisfy the traveling wave equation. In the sense that if you launch this cosine type wave into our transmission line, then as time changes, then the traveling wave, depending on whether this is plus or minus traveling wave, this function will either go towards the right or towards the left. It'll actually travel towards the left or towards the right without losing its shape through the transmission line. And so some of these definitions that are handy in transmission line equations we call omega when things are in this form. So this guy, omega, is called the angular frequency, and that's 2 pi times f. F is the frequency of the sine wave, cosine wave, so f is in hertz. And omega is in units of radians per second. Okay, and then beta, and that's this constant next to z, is so-called propagation constant, is the, and omega over beta is called the phase velocity. And that's equal to 1 over square root of LC. So I'm going to put a circle around this thing and say, remember this. There's a few things here that I'll call out that's worthwhile remembering. And the usual symbol for this is u sub p. But this is the same thing that we talked about here. We calculated this is the velocity of the wave or the function, the velocity of the function as it's traveling through the transmission line. So if you have a cosine, sine, or a combination thereof with this type of function, omega or beta, omega over beta gives you the velocity that this function travels through the transmission line. And incidentally, the change in omega with respect, the derivative of the omega with respect to beta is called u sub g. So this is u sub p. This is u sub g. U sub p, u sub g. And this is called the group velocity. And if this group velocity is a function of frequency, then you have something called dispersion. And dispersion means that the velocity depends on the frequency of the sine or cosine wave. That's all I'll really say about it. I mean, I just wanted to call it out for now. We're not going to really touch this, but if you, at the moment, but it's actually a pretty important effect and something that's kind of a pain to deal with. The reason for this is in a lot of transmission line forms or a lot of transmission lines, you have square waves going through your transmission line. And if you guys remember that, if I have a square wave in the time domain, so if I just have like a rise time here, this rise time, if I transform this into the frequency domain, this will have like be represented by a bunch of different frequencies. So basically this is made up of a bunch of cosines or sines to make up this square wave, and we can segment it in the frequency domain in different frequencies. What would happen if you have dispersion is these different frequencies would travel at different velocities at different speeds through the transmission line, and that means even if you don't have loss, when you're traveling through the transmission line, this square wave, it was going to start changing its shape in time as it travels through the transmission line. It won't lose its amplitude, but it'll just start changing its shape, which is a pain to deal with, because usually what you're trying to do in a digital system is you're trying to preserve the shape of your signal. So that's all. I'll talk about dispersion here, but I thought I'd mention it for completeness sake. Okay, so this is all about what would happen in a traveling wave if we had, what would it look like if we had cosine or sine forms, which we will use a lot because the math is a little bit easier. We know what to do with cosines and sines. And also, again, it's representative of a lot of the functions that we'll see. So something that gets a little confusing, so pay some attention here, is something called a phasor notation. You might have run into phasors before, and this is a notation that's used to make the math a little bit easier, because we can only need to keep track of a fewer things during the calculations, but it can get confusing. So let's just begin with a normal notation. If we have a voltage that's a function of position and time and has this traveling wave function, we can say it has a shape. Let's call that voltage has a cosine of omega t minus beta z type function. And let's say it has an amplitude v0 plus. So this is a traveling wave function that has a phase velocity. So this has a phase velocity of omega over beta, and it's traveling in the plus z direction. So that's what we know. This is a cosine wave traveling in the plus z direction. It has an amplitude v0 plus and a phase velocity omega over beta. Okay. Or it's possible that there's another voltage source that, so let's call this V, what should I call this? Or, another case, let's call this V1, let's call this V2, say. So you have T that has a amplitude V0 minus, and it's cosine of omega t plus beta z. And this is also has, this waveform also has a phase velocity, this cosine wave velocity of omega over beta, but it's traveling in the minus z direction. And the way I know which direction it's traveling in, if this is a minus sign, it's traveling in the plus z direction. And if this is the plus sign, it's traveling in the minus z direction. Okay, so that's my, either way, that's my voltage waveform. Now I can write this thing. Let's write it in another way. And this is where it's good to start getting familiar with complex notation. Okay, so this is V at zt. I can also write this as being the real part of V0 plus e to the j omega t minus beta z. And that's equal to the real part of, whoops, V0 plus cosine of omega t minus beta z plus j sine of omega t minus beta z. And so the real part of this is just equal to that. So it ends up being equal to V0 plus cosine of omega t minus beta z. Okay, so if we assume that omega is constant, what does that mean? That means we have a single frequency that the cosine or sine wave is in. It doesn't have multiple frequencies and it's not changing. Then we can use something called the phasor notation. And what do we do there? Well, we use, when we write our V of zt being a real part of, so we write it again in this form that we had it up here. And again, this thing is just a different way of writing Vz of t is equal to V0 plus cosine of omega t minus beta z. If we just, this real part of V0 e to the j omega t, it's just the same thing as writing this. Okay? So if my omega t is constant, we can use this thing called the phasor notation. And the whole idea behind the phasor notation is that it allows us to sort of momentarily get rid of some of these things and then insert them back in. So what we can do to use this phasor notation is we can stop using real and e to the j omega t when we do our calculations, and then at the end of our calculations, when we're all done, we can sort of reinsert those back in. So in phasor notation, this would look like v of z of t is v0 plus e to the minus j beta z. So what I did was I forgot about real part of. Okay, I know I'm going to reinsert this real part of back at the end. And then I forgot about e to the j omega t, because I know I'm going to re-multiply whatever I have at the end of my calculation with e to the j omega t, but it's just not going to change. I've assumed that omega is constant, so I don't have to keep track of e to the j omega t. So I can use this as a surrogate, or as a way to reduce the number of things I'm keeping track of. I can just forget about this real part, forget about the j omega t. These are the two things that are going to change in my calculations. Keep track of this, and I'm doing my calculations in this phasor notation, and then at the end of my calculations, I'm going to plug it back in. Okay, so let me use an example of what I mean by this phasor notation. So this is an example of phasor notation. So let's say I want to take the derivative respect to time of a waveform. So this is the example. Okay, so I have a waveform V0 plus cos omega t minus beta z, and I want to take the derivative of this with respect to time. Okay, that ends up being, if I take the derivative of that, ends up being minus omega V0 plus sine of omega t minus beta z. And that's equal to the real part of j omega V0 plus e to the minus j beta z e to the j omega t. Okay, so to write this in phasor notation, so to write this in phasor notation, I'm going to drop mention of real part of, and then 2, drop the e to the minus j omega t. And so in phasor notation, I just end up, this is just going to look like, so in phasor notation, this derivative is just going to look like, so derivative with respect to t of v0 plus cos of omega t minus beta z is just going to look like j omega v0 plus e to the minus j beta z. And I'm going to call this the phasor And the sign for this is going to be V0 hat plus Z. So these two are just going to equal to each other. And again, this is just a way of trying to simplify the math. So for example, one way this simplifies the math, as you can see in this case, if I have the derivative of, I have this derivative of V0 plus cosine of omega t minus beta z, okay, is just equal to j omega times the same thing in phasor notation. So in phasor notation, j omega v0 plus e to the minus j beta z. So in phasor notation, the derivative with respect to t is going to look like we're just multiplying by j omega. So this is in phasor domain, in phasor notation. And integral, I haven't shown this, but integral of with respect to time is equal to 1 over j omega. So it makes life easy when we're doing math, etc. Again, it's not like we're going to, I don't know, it's not like we're doing a frequency transformation or something like that. It's just a way to sort of keep track of, or not keep track of, but make calculations a little bit easier. Okay, so another look at it could be when we're doing the same thing for current. So let's say we can have a phasor notation for current also, I0 plus Z hat. So whenever you see this hat on top of a capital V or I, you notice you have phasor notation in this class. I'm going to draw this hat a little easier, better. And that's equal to I0 plus e to the minus j beta z. Okay, so now that's my phasor. When I tell you this is my phasor, let's say I want to go to my quote-unquote real current now, to go back to value from phasor notation. I multiply, so I'm going back from, at some point I'd gone from the real function to the phasor notation to do my stuff. I ended up with this in phasor notation. Now to actually look at the waveform, I need to take it out of phasor notation, so I just need to retrace my steps. So step 1, I multiply this thing by e to the minus j omega t, because we've taken that out. And step 2, we take the real part of it, because we were looking at the real part of the expression. So what this looks like is real part of I0 plus e to the minus j beta z e to the j omega t. So I multiplied by e to the j omega t, and I'm taking the real part of it to get back to the actual function. And that's equal to real part of I0 plus e to the j omega t minus j beta z equal to real part of I0 plus cos omega t minus beta z plus j sine of omega t minus beta z. And that's equal to I0 plus cos of omega t minus beta z. So That's my actual function, okay, which is equivalent, absolutely equivalent to this phasor notation, except again, I was like getting rid of this j omega t and this real part stuff so that in my calculations I could, make my life a little bit easier, not to worry about these things. Okay, so, and we'll see example, we're mostly working on using this phasor notation when we're doing calculations, so you'll get lots of practice or lots of views of this. Okay, so let's say we have now, using this phasor notation, let's say you have a waveform, a current waveform, I0 hat in phasor notation plus Z, and I0 minus Z. This is simultaneously going through your transmission line. These are the currents. So when we're looking at, we know the derivative of V respect to Z is minus L di dt. So because if we're operating in phasor notation, we can just say, instead of this derivative with respect to t, we can just replicate or replace that with j omega. So we can write this in the phasor notation as derivative of the voltage phasor is equal to minus L j omega, the current phasor, the plus version of the current phasor. Okay, so let's see. So the derivative of, and then we know V0 hat plus of Z is V0 plus e to the minus j beta Z. So taking the derivative of this with respect to Z, is minus j beta V0 plus e to the minus j beta Z is minus L j omega I0 plus Z. So I can, let's see, what can I do? I can cancel these j's here and the minus signs. Then I can have beta V0 plus e to the minus j beta Z is omega L I0 plus Z this is just the phasor notation again, so it's beta V0 hat plus Z is omega L I0 hat plus of Z. So in phasor notation, V0, so this is the phasor notation for the voltage divided by the phasor notation for the current. So voltage over current ends up being omega L over beta. So this is the relationship between the current and the voltage of a transmission line. So if you look at this thing, voltage over current looks like an impedance, and this is called the characteristic impedance of a transmission line. So that's something else that you should also remember this. But when I say remember this, I mean remember this like forever. So when you're looking at this velocity of where do they have it? I had the velocity, phase velocity, or the speed at which a waveform goes through a transmission line. That is 1 over square root of LC. That's worth remembering. You'll if you're dealing at all with transmission lines, which you will at some point in your work, maybe a lot, maybe a little, but at some point you will come across this again, which is this phase velocity, or the velocity of the waveform through a transmission line, is 1 over square root of LC through a lossless transmission line, 1 over square root of LC. And then the characteristic impedance is even more important, as basically this ends up being this function. Okay, so now looking at it some more, this so Z0, this characteristic, we're going to call this characteristic impedance. We're going to call this capital C Z0 is omega over beta times L. I'm just, whoops. So I'm just writing this over here. And so omega over beta, this guy, is the phase velocity. So this just looks like phase velocity times L. The phase velocity was 1 over square root of LC. Multiply that by L, and I get square root of L over C. So in a lossless transmission line, the characteristic impedance of that transmission line is going to be square root of L over C. Okay, so remember this. This is like a very important function.